Hi, my name is Max Sturgis. This is Francis Parento. On the camera is Libby Aldrich, and Tyler Vandals is also in the room. Frank and I are part of the AP Physics class, and those three are part of the multivariable class, and this is our final project for the year. We were asked to use one of the AP Physics problems and actually do it out. So for later years, Mr. Carey could have the possibility of actually using this lab for his class. So the problem is the 2009 AP Physics C Mechanics Free Response questions. If you look up here, this is a quick diagram of what we were asked to do. We'll talk about the questions later, but first we want to show you guys actually what we did. We were asked to actually build the experiment, and so what I came up with was to actually build a pendulum itself, because that's what's asked for in the problem. And to do that and everything, the problem requests that is of non-uniform density. So one of the first things we did was actually put a 100-gram weight on it to make a non-uniform density, away from the pivot point and away from where the center of mass would have been, to change it pretty significantly. In order to make it move pretty nicely, what I decided to do is, if you can see, it's kind of hard to see, but a little screw I'd screwed into it, and it's stuck in the middle of a yo-yo right here, inside of it, which creates a perfect pivot point, essentially frictionless. Next, we used a clamp to put on here to make it, stuck it on here, and voila, we have a perfectly balanced thing and a pendulum that swings. So this would be a pretty cool experiment for anyone to do. You have to, come up with your own pendulum to make, and this was our variation of doing one.
All right, so now back to the problem. So the first question, question A, part 1, asks by applying the appropriate equation for the upward motion to the bar, write the differential for the angle theta the bar makes with the vertical. So we're gonna, first of all, we have to acknowledge that torque is equal to I alpha and is also equals to the force times the radius. So knowing that, and knowing that the torque is negative because the force is downward on the pendulum, we can come up with the equation negative mgx sine theta is equal to I alpha. And therefore, knowing that, we can express theta, alpha, as a second order derivative of theta, where negative mgx sine theta is equal to I d squared theta over dt squared.
Part 2 of it was asking us, by applying the small angle approximation to our differential equation, calculate the period of the bar's motion. The small angle approximation, we know that sine of theta is equal to theta when the angle is less than 15 degrees. Therefore, we can take that, instead of using sine of theta, like we did here, we can now just use theta, making negative mgx theta is equal to I times the quantity of d squared theta divided by dt squared. We also know that the coefficient of theta, negative mgx, is omega squared. Therefore, omega squared is equal to mgx divided by our rotational inertia. We can next plug that into our period equation, where our period is equal to 2 pi divided by omega. Therefore, our period is equal to 2 pi times the quantity times the square root of our rotational inertia divided by mgx.
So that's for part A. Now, part B asks to describe an experimental procedure we could use to make the additional measurements needed to determine the inertia of the pendulum. Including we would use our measurements to obtain the inertia, and we would minimize experimental error. So we came up with 2 examples to figure out the inertia of the pendulum. First of all, we could displace the bar by a small angle, and using a timer, we could calculate the time it takes for the pendulum to complete 10 full oscillations. And then we could divide that number by 10, which would give us roughly what our period is. Then, knowing that the period is equal to 2 pi times the square root of I over mgx, we could find our inertia, because we also know the mass of our pendulum and the center of mass of the pendulum. So that's the first example. Now, the second example we could use to find the inertia is using a Florida gate. which is something we worked a lot this year in the physics class, and that would actually give us a more precise period. So how we would do it is we would place the flow gate under the pendulum at the point where it's completely vertical, and we would make the pendulum oscillate, and we would just record the data on the computer, and then we could average the data we get, and we could find again the period. And then knowing the period, we could use the same calculations we used with the timer, where we could just use the fact that the period is equal to 2 pi times the square root of inertia over mgx. And knowing the mass again and the center of mass, we could find again the inertia of the pendulum.
Numbers are part C is they ask us, now we suppose that we are not given the location of the center of mass of the bar. We ask to describe an experimental procedure that we can use to determine it, including the equipment we could use. This is a little difficult one, trying to figure out the center of mass without, we're not giving it. How can we do that? And so we came up with the idea that if we replace the bar on top of a fulcrum, such as a prism, we can adjust the bar to the point where it's perfectly horizontal, perfectly even, the mass is equally distributed. And that point where it's resting on the fulcrum, that would be where our center of mass was located. That took a little while to figure out. Example 2 is to place the bar near the edge of a desk or table. Show with this meter stick right here. Now what we would do is have it at a certain angle and measure where it would be until it would actually start to fall off the table. And that would again allow us to know where the center of mass, that point where it would start to fall off, is where our center of mass was located. So this problem was actually very fun to do. It was, it's a great problem we chose. I actually spent a good hour going through multiple AP Physics free response problems to find out the one we wanted, and I thought this would be fun. We could build it, we could demonstrate it. It's got 2 parts of strictly calculus and 2 parts strictly physics. Therefore, it was a perfect problem to use for the multivariable and the AP Physics class. It was fun, it was a lot of work, and again, I'm Max Sturgis, this is Francis Prento, we have Tyler Vangelis, Libby Aldridge on the iPad, and we are members of the AP Physics and multivariable classes here at Holderness.